Hello and welcome to our Physics 141 Project 2. In this video, we will be investigating the force and energy put into a pedal stroke on a bicycle and how they will affect the velocity and angular velocity of the bike and wheels. Let's get started. Here is our video, shot in slow motion at 240 frames per second. Using what we know about the cyclist and the slope, we will determine the forces involved, the work done by the cyclist, the power produced by the cyclist, and both the velocity of the bicycle and the angular velocity of the wheels. We'll be using the dynamics lens since we will be dealing with forces and acceleration. First, we will draw a picture and label our knowns and unknowns. The slope is 7.56 meters long, with a horizontal component of 7.5 meters and a vertical component of 1 meter, and an angle, theta, of 7.6 degrees. The cyclist, bike included, weighs 75 kilograms and travels the length of the slope in 1.8 seconds at a constant velocity. To solve this, we create a free body diagram. Here is our free body diagram. The force of gravity, Fg, acts on the cyclist in the negative y direction. However, the axes we will use will be parallel and perpendicular to the slope for the sake of simplification. The force we're looking for is in the positive x direction parallel to the slope, and will be referred to as F push. F push is just the force needed to overcome the horizontal component of gravity plus the rolling friction against the bike wheel. The force of rolling friction is equal to the normal force, Fn, times the coefficient of rolling friction, mu. The normal force happens to be equal to the component of gravity which is perpendicular to the slope. Now we plug in the numbers. Fg is equal to g times 75 kilograms, which is 750 newtons. The normal force is equal to Fg times the cosine of theta, which is 743 newtons. F push is equal to Fg times sine theta, which is 99.2 newtons, plus mu, 0.004, times the normal force of 743 newtons, which is 3 newtons, coming out to 102.2 newtons total. So F push is equal to 102.2 newtons, and that's the force which needs to be constantly applied in order to overcome gravity and continue at a constant velocity up the slope. The work done by the cyclist is equal to the force times the distance traveled, or 102.2 newtons times 7.56 meters, which equals 772.6 joules. The power is equal to the work done over time, which is 772.6 joules divided by 1.8 seconds, which equals 429.2 watts. Now for the velocity. 7.56 meters over 1.8 seconds comes out to 4.2 meters per second on average, which is supported by tracking data along with the power output of the cyclist. So we did something right. As for the angular velocity, the wheels have a diameter of 27 inches, which is equal to the radius of 34 centimeters or 0.34 meters. Given a tangential velocity of 4.2 meters per second, the angular velocity of the tires is equal to the tangential velocity divided by the radius, or approximately 12.4 radians per second.